I've explained in the first lecture that there are two parts, two sides to a smart contract, an on-chain part and an off-chain part. The on-chain part is about validation. It allows nodes to validate a given transaction and decide whether the transaction is valid and whether it's allowed to consume a given UTXO. And the off-chain part lives in the user's wallet and constructs and submits suitable transactions. So both are important topics, and we have to master both in order to write smart contracts. But for now, I want to concentrate on the on-chain part. So let's recall the extended UTXO model, where the idea was that we introduce a new type of addresses. So the type of addresses used in the simple UTXO model is so-called public key addresses, where the address is given by a public key or the hash of a public key. And if a UTXO sits at such a public key address, then a transaction can consume that UTXO as an input if the signature belonging to that public key is included in the transaction. And what the eUTXO model does is extend this by adding a new type of addresses, so-called script addresses, that can run arbitrary logic. And then when a transaction that wants to consume a UTXO sitting at a script address is validated by a node, the node will run the script and then, depending on the result of the script, decide whether the transaction is valid or not. And recall that there were two more additions. So one was that now instead of just having signatures on transactions, we have so-called redeemers, arbitrary pieces of data. And on the UTXO side, on the output side, we have an additional arbitrary piece of data called datum, which you can think of as a little piece of state that sits at the UTXO. Finally, we have the context. And then I explained last time that there are various choices what this context could be. It could be very restricted, just consisting of the redeemer, or it could be very global, consisting of the whole state of the blockchain. But as I said, in Cardano, it is the transaction that is being validated, including all its inputs and outputs. So there are three pieces of data that a Plutus script gets. The datum sitting at the UTXO, the redeemer coming from the input under validation, and the context consisting of the transaction being validated and its inputs and outputs. So in a concrete implementation like Plutus, these three pieces of data obviously have to be represented by some concrete data type, a Haskell data type. And as it happens, the choice was made to use the same data type for all three of them, at least at the low-level implementation of Plutus. There's also a higher level version that we will look at later in this lecture, where it is possible to use custom Haskell data types for datum and redeemer, which is often much more convenient because you can choose appropriate data types that play well with the domain you're working in. However, there is a price to pay for this convenience and this higher level of abstraction, namely performance, because if you make use of that, then you have to serialize and deserialize between your custom types and this underlying low-level data type, which in practice can make a difference. So some projects that have tried to build something on Cardano using Plutus have actually not chosen the convenient high-level possibility to use custom Haskell data types, but instead worked with this low-level data type directly for performance reasons. Hopefully over time the Plutus compiler will be optimized and the overhead of using the more high-level techniques won't be so bad anymore. And in this course I will mostly use the high-level way. But keep in mind that if you're actually building a project, it might be necessary to go down to the low level. So let's start by looking at this data type that is used to represent all three pieces of data that the script receives: datum, redeemer, and script context. Normally, when I want information about a Haskell type of function, I have easy access to that from within the REPL. So for example, if I want to learn about the maybe type, I can do :doc maybe, and I get the headoc documentation for maybe. It's not very nicely formatted, so these markdown annotations just appear as plain text, but it's already quite nice. However, the same doesn't work for Plutus types and functions. If I import the module where built-in data is defined and ask for documentation for built-in data, then the REPL tells me it can't find any. And that has to do with the way Plutus compilation works. So the way it works is we write a Haskell program, then the normal GHC, Glasgow Haskell compiler pipeline, is used to compile that Haskell function to the intermediate language called Haskell core. And then the Plutus compiler takes this core and compiles it to Plutus script. And this is done via a so-called plugin. And this plugin causes some disruptions to the normal conveniences we are used to in Haskell. For example, it's less convenient to work in the REPL, which means in order to work with Plutus, we need some other way to access documentation. And the Plutus libraries are also not hosted on Hackage, where you normally find documentation for all the standard Haskell libraries, but hosted on some GitHub repos. And even if you go to these GitHub repos, you could browse the source code, but you don't see nicely formatted headoc pages. So therefore, for this course, we made the documentation of the Plutus libraries easily available. Here I am in a local dev container. My colleague Robertino explained in the first lecture how you can set that up. And from the local dev container, I just have to invoke serve docs, and then it asks me whether I want to open that in the browser. And there is documentation of all the relevant Plutus libraries. And I can simply search for functions or types by Control S. So if I press Control S and start typing built-in data, then I find it, and we see it's in several modules. But for this course, we're using Plutus version 2, which became available with the Vasil hard fork last year. So if I click on this, then I have nice headoc documentation for the built-in data type. If instead you're working in Demeter, you can also make that work. So if you open a new terminal, you once need to run a script. So you can just do scripts and then alias server docs Demeter. And that will make the serve docs command available. So if you close this and reopen a terminal, then now the serve docs command should also be available in Demeter. In my case, it immediately works. You probably first have to open the port. So on this dashboard here for your workspace, under the basic information for your workspace, you see this section about exposed ports, and I added port 8000 there to make this work. So once you've done that, and then you start the server with serve docs, you can open in browser and you get the same that I showed you before in the local environment. There is no constructor exposed, but there are conversion functions from another data type called data to this built-in data type. back and forth. And if you read this information here, you will find that built-in data is meant for use in on-chain Plutus code. So your Plutus validators in particular are written using this built-in data type. But the way to actually get the value of this type is normally via one of these conversion functions. So let's look at the data type from which you can convert to built-in data next. And here we have the constructors exposed. So let's look at them briefly. So there's a constr constructor that takes an integer and recursively a list of data. Then there's the map constructor, which takes a list of pairs of data, which you can think of as keys and values, hence the name map. The list constructor, which recursively takes a list of data. Then an I constructor for numbers, for integers, and a B constructor for strings, or rather byte strings. And for those of you who are familiar with the JSON format, this data type is very similar. The constructors are not exactly the same, but similar. So like in JSON, you have numbers and strings and lists and maps and so on. And the reason, or one of the reasons why JSON is so popular, is because you can encode almost arbitrary data as JSON. The same is true for this data type. Almost arbitrary data can be expressed as a value of type data. And this is exactly what we want for Plutus, because when I explained the extended UTXO model, when I talked about datum and redeemer, I said that should be arbitrary pieces of data. And the data type allows that. We can play with this type in the REPL. So I'm in this week's code folder and I fire up a REPL with Cabal REPL. Now in order to get access to the data type, I can import plutus.v2.ledger.api. So if I do :I for info and ask for information about the data type, then I basically see the same that we just saw in the source code. And here we also see where it is actually defined. Now I can play with this, so I can try to define values of this type. So for example, I can use the I constructor with an integer, so I42. I can ask for the type, and that is indeed of type data. If I want to use the B constructor, I need a byte string, and the easiest way to quickly get a byte string is to activate an extension, a GHC extension that's called overloaded strings. And what that overloaded strings extension does, normally in Haskell, literal strings are of type string, the Haskell string type, which is just a synonym for lists of characters. But with this extension, I can use literal strings for other string-like types as well. And one of those string-like types is the byte string type. So now that I have this extension, I can use the B constructor, for example, Haskell, and I get, again, something of type data. And of course, I can also use the more complex constructors like map. So if I have map, and now I need a list of pairs of data, key value pairs. So for example, one key could be I42 and the value could be B Haskell. And the key can also be more complex. So I can, for example, use the list constructor, I don't know, I0, and as value I1000. And again, I get something of type data. Now let's look at our first example of a very simple, arguably the most simple smart contract. So you'll find that in this week's code folder in a module called gift. So it starts with a bunch of extensions that are necessary and some imports. And now the validator that we're going to define, the Plutus script, is just a simple Haskell function. I will explain later how this Haskell function gets translated, compiled to Plutus core. So as we discussed before, this function will take 3 arguments, one corresponding to the datum, one corresponding to the redeemer, one corresponding to the context. So again, the datum is supplied with the UTXO that has been created by the transaction that produced the UTXO we now want to consume. The redeemer comes from the spending transaction, the consuming transaction that wants to use that UTXO as an input. And the script context represents the whole transaction with all its inputs and outputs. And as we just discussed, all 3, datum, redeemer, and script context, are represented in this low-level Plutus by the same data type, built-in data. Now, what about the return type? And that might come as a surprise. It's just unit. So the unit type in Haskell, you can ask for information in the REPL. It just has a single constructor, which is also called unit, and it has no arguments. So if we ask for the type of the value unit, then we see unit is of type unit. And this is the only value of this type. So this is a Haskell data type that has exactly one value, namely unit. And this is similar to the void type in other, maybe more mainstream programming languages, like Python or Java or C++ or C#. Now, if you are somewhat more familiar with Haskell, you will be surprised about this signature, because in Haskell it's very rare that we have a function with a return type of unit. In mainstream programming languages, you often see functions or procedures with a result type of void. And the value of such functions lies in the side effects. The end result is not interesting. A void result, or in the Haskell case, a unit result, carries no information, as I just said. We know what the result of the function will be. It will be unit. So why would you bother writing such a function? Now, in other languages, the reason is that in other languages, functions can have arbitrary side effects. So a function with return type unit in Java, for example, could write something to the screen, or do networking, or access the hard drive, or whatever. In Haskell, that's not possible, not with this signature. That would be indicated by an IO to indicate that it has side effects. So this is very unusual. And the way it works is there is one thing that a Haskell function can do apart from returning a result, and that is it can have an error or an exception. It can fail. So the way validators work at this low level is that if there's no error, then validation passes, and if there's an error, then it fails. So this is arguably the easiest, the simplest validator we can possibly write. The 3 underscores indicate that we completely ignore the arguments. So we don't care about the datum, we don't care about the redeemer, we don't care about the context, and we just return unit without having or producing error. So that means it always passes. It doesn't care what datum, redeemer, context are, it always passes validation. And what does that mean for the corresponding script address? So recall, a script address is more or less the hash of the validator. So I'll show in a second how we turn this Haskell function into Plutus core script. And then if you take the hash of that script, you get the address, the script address. So what would it mean to have an output sitting at the script address? Well, it would mean that arbitrary transactions can use that output as input. Arbitrary because it doesn't matter what redeemer is used, it doesn't matter what datum was used at the output, and it doesn't matter what structure the transaction that consumes that input has. So that's why I called this module gift, because if anybody sends funds to this script address, then anybody else can immediately consume that output and use it for their own purposes. So if you send ADA to this address, it's a gift. Anybody can immediately take it. Now that we have defined this very simple validator function in Haskell, we want to compile it to actual Plutus core script. And that happens here. And unfortunately, this uses an advanced Haskell mechanism called template Haskell. And you can see that here with these $, and these so-called Oxford brackets. Now, what does this do? So if we hover with the mouse, we can see the type of compile. So compile is a function that takes a splice of type A and turns it into a splice of compiled code A. So what's a splice? You can think of that as a piece of source code. So in the first approximation, you can think of it as a string, the string that actually represents the source code. So this make gift validator is the Haskell function we just defined. So that's a function. But compile expects not a function, but a piece of source code that represents a function. And that's what these Oxford brackets do. They do a so-called quote, so you can quote a piece of Haskell code to get to the actual source code or syntax tree that defines it. So this here is basically as if we had taken this source code here and written it directly here. Now compile takes this piece of syntax and produces another piece of syntax, but now of a different type. I mean, earlier, this piece of syntax here is Haskell, this Haskell function, and it turns it into a piece of Haskell syntax that represents Plutus core expression. Now this make validator script expects compiled code, the right type, built-in data, built-in data, built-in data unit, and produces a validator. But compile doesn't give us a function of that type. It doesn't give us compiled code. It gives us syntax for such a function. So now we must do the opposite thing that we did here with the Oxford brackets. We must splice this syntax back into this position here to get actual compiled code. So this is this $, that does the splicing, that basically has the effect as if instead of this expression, we would have typed that syntax tree that we want to splice in directly here in the source code. So this result of compile will be some complex syntax tree representing compiled Plutus core. And the $, makes it so as if we had typed this complicated syntax tree directly here at that position. And then takes that and turns it into an actual validator. But as I said before, it's not really important to understand this template Haskell mechanism because it's always the same when you work with Plutus. So you can just copy paste it. One important thing is that normally in these Oxford brackets, you can't reference anything outside the brackets. So you must put everything, the whole expression or function or whatever that you want to quote inside the brackets. Now in our case, that would have been simple because the function itself is just these few characters here. So we could easily not have bothered defining an extra function for that and directly written this here inside the brackets. But of course, often validators are much more complicated. And not only that, you also maybe want to split them into several functions. Maybe you want to reuse some functions, or you want to use library functions that are defined in other modules and so on. And that would normally not work. Normally, everything needs to be included in these brackets for this template Haskell to work. However, it works if the functions
are inlineable, because then the Haskell compiler will inline them inside these Oxford brackets. And that's why we have this pragma here, this inlineable pragma. So that tells the compiler that it's okay to inline this function, and then the effect will be the same as if we had by hand typed everything that we reference here directly inside the brackets. So you will see this inlineable pragma all over the place in Plutus libraries, and that's always a good indication that something is meant to be compiled to Plutus core, meant to be used on chain. Now, having that, we can actually look at the value of validator in the REPL. Unfortunately, it's not very enlightening. I mean, we see it works, so compilation seems to have worked, but we just see this opaque script word here. We can try to unwrap that a bit. So if we ask for information on validator, we don't get any. Oh yeah, we must, it's a Plutus V1 ledger script, so let's import that. Let's try that again. Okay, now we see validator is just a new type wrapper around something called script, and we get to that with get validator. So we can try get validator of validator. Okay, now we get a script, but we still don't see anything. So let's ask for information about script. We say that's another new type wrapper, this time around something of type program. And we can unwrap the script into a program with unscript. So let's try that. Unscript, get validator. And now we actually do see something. So now we see this expression. And for those of you that have seen lambda calculus before, this is a version of the lambda calculus. So Plutus core script is a version of lambda calculus. And here we see the actual representation of this lambda term. So we see that the compiler indeed compiled something, and it compiled this simple Haskell function into this still quite simple lambda expression. Now by itself, the validator is not very useful. So depending on how we actually want to interact with the contract, often it's necessary to have it in serialized form, because other tools, for example, the Cardano CLI, need a serialized form of the validator to work with it. And this is the last part of this module here. So it calls a helper function, write validator to file. This is actually not a standard Plutus function. That's a function that we implemented for this course. And you find that in the utilities module here. So there is a utilities module here in module serialize. We have this write validator to file. So it just uses a bunch of library functions, Haskell library functions, does some byte string manipulation and serialization to do that. So it takes a Plutus validator, sorry, this one. So it takes a file path and a Plutus validator, and then has the effect of serializing this validator and writing it to the file given by this file path. So in this case, we write the validator to this file, assets, give Plutus in the week 2 code folder. So we can call that from the REPL. So we can just say save file, and it writes it there. You can actually check. So some examples are already defined there. So that should be give Plutus. We can actually look at it, and it's in a nice textual format. So it tells us it's a Plutus script, Plutus version 2, and this is the actual serialized contract. So in this case, it's very short. More complicated contracts, of course, can be much longer. But remember, this is arguably the simplest Plutus validator you can possibly write, because it doesn't do anything. It completely ignores its arguments and just immediately returns unit. Now that we have seen the first example of a Plutus script, let's look at the second example, which is almost as simple. And that's in module burn. And before we look at the definition of this make burn validator, let's just note that these two functions are exactly the same. So once we have defined our Haskell function, we can compile it into a validator with the exact same template Haskell. The only difference is that instead of make gift validator, we now use make burn validator. And then we can also serialize it again using this helper function write validator to file. So where the first example, the gift, was a contract that always succeeds. So no matter what redeemer you throw it at, it will always say that it's okay to spend the UTXO locked at that script address. Now we want to do the opposite, validator that always fails. So something sitting at that address will forever sit there. It will never be possible for any future transaction to spend that UTXO. And as I said before, the only way to do that is to produce an error. And we can simply do that with the error function. So before we returned unit, and now no matter what the arguments are, datum, redeemer, script context, we always produce an error. Now, error is a common function in the Haskell prelude, and normally it takes a string as argument. And then it produces an error, and the string is the error message. So for those of you who are a bit familiar with Haskell, this looks weird because here error doesn't take a string, it just takes a unit. And if we check the type, we see that indeed error has type unit to whatever type you want. As I said, in normal Haskell, instead of unit, it would say string. So that's a bit strange. And the reason is that this is not the error you are used to from normal Haskell. And if you notice here, the pragmas, the second one here says no implicit prelude. So normally, when you write Haskell code, you have to explicitly import libraries you want to use, with the exception of the prelude. The Haskell prelude is by default always imported automatically, and you don't have to list it here in one of these import statements. But you can override the default with this no implicit prelude pragma. You can then still explicitly import it if you want. We have done that here. We import the IO type because we need that for the save val here. But everything else from the prelude is not imported into this module. Instead, we import something called Plutus DX prelude. And from that, we actually import this error function. So why do we need a special prelude for Plutus? Well, one of the reasons, maybe the most important reason I hinted at earlier, the problem with this inlineable. If we want to use library functions in our validators and then compile them, they must be inlineable. But of course, when the Haskell prelude was created, nobody had ever heard of Plutus. So a lot, or probably most of the functions defined in the Haskell prelude are not inlineable. So they would be useless for on-chain Plutus code. But of course, we want to have functions in the prelude that we can reuse. So the Plutus team basically copied the standard Haskell prelude and made everything inlineable. This, of course, is not strictly speaking true. So a lot of things from the actual Haskell prelude are missing in the Plutus prelude, but a lot of the most common functions you are used to from the Haskell prelude are also in the Plutus prelude. Sometimes it can be a bit confusing though, because not always do these functions in the Plutus prelude have the same signature you're used to from the Haskell prelude. And error is a case in point. So in the normal Haskell prelude, as I said, it takes a string argument, and in Plutus, it only takes a unit argument. There are variations of error where you can also give debug error messages. I think it's called trace error, so we could replace this with trace error. Then we have to import that as well. Then we can give an argument. So we could alternatively use this. Now we get an error message because it expects a built-in string, but it is now of type string, a normal Haskell string. But with the same trick we saw earlier by using this language pragma overloaded strings, we could remedy that. Now we, of course, don't have to import error anymore. Right, so there is this variation if you want to give an error message. This all just means that you have to be a bit careful. So that can sometimes be confusing. You have code that looks perfectly fine, but it doesn't compile and you get errors. And sometimes the cause is that you use a function that exists both in the standard Haskell prelude as well as in the Plutus prelude, but with different signatures. So that can sometimes be confusing.